Having said that, I would like to start with the first talk by Emirhan Evin from Middle East Technical University, who's going to talk about adjoint-based elastic shape optimization of a slender mounted wing, of a slender wing mounted on a loitering munition. So it is an online talk. This right? Emirhan, are you there?
Emirhan, thank you for introduction. It's me, Emirhan Evin. I am doing master study at Middle East Technical University, and also I am working as an aerodynamic engineer at Roketsan Missiles Industry. Today we will be talking about a aeroelastic shape optimization of a slender wing. Here my outline. First, I will introduce you the problem, and then I will share you my problem definition used in my thesis study. Then we will slowly propagate into the first fluid domain. Then we will see the structural properties and structural domain. Then we will combine these two together and we will do some FSI analysis. After that, I will show you the last point in my master study right now in obtaining the adjoint solutions. Also, I will share you one both problem I faced during structural deformation. Here we will see the tube or air-launched munitions have difficulties while moving their wings or control surfaces after the launch because they need to overcome the drag force, and also the final deflection or bending moments must be low such that the friction drag on the mechanism shouldn't increase. This problem becomes more important with the increased popularity of the loitering munitions because right now, as you can see in two pictures, these have huge wings and they need to overcome a lot of drag while opening. So I will design the problem. Here we can see my configuration, conceptual configuration. The main objective is to study in this thesis to minimize drag, while we need to keep the lift fixed because I don't want to go over the design process again. We need to reduce the tip deflection, or we can say that we want to reduce the bending moment at the wing roots because it's also prevents us to open wing successfully. Since it's already designed, also you need to enter a tube. You can change your span, or you can change your chord length. Also, since the wings collide on top while put in the tube, you need to prevent the wings collide during the opening phase. Initial design has same airfoil all over the wing is ST-737, and these are the other properties. For the structural modeling, I am using a single template. As you can see, these are the properties. For the leading edge, it has 8 mm thickness. At the trailing edge, it has 6 mm thickness. You can see it on the wing inside. Here, the orange one, the structural model, inserted in the fluid domain on the inside the wing. Also, I tried some geometries like thick hollow shell or rib spar formation, but these models failed. For the fluid domain, as you can see, I use point-wise software to mesh generation. Also, the fluid domain mesh is generated unstructured. I used three sources to cluster the mesh close the body and refine the expansion of the certainty force field. Also, we can see how the source aligned inside the domain. Here the slides, we can see source actions. Also in the right bottom, we can see the boundary layer generated. For the flow solution, sorry, it's a little bit laggy. For the flow solution, I create 4 different fluid meshes. As we can see, it starts from 20.66 to 24. Okay. And you can see the mesh is covered to a point where after increasing the number of cells can change the mechanism mode. I choose the 19.5 million mesh considering my accuracy and also the convergence speed. Here we solve the RAS equations with SSD modeling. The analysis are done at 0.1 mark. Also, here some other properties given, like numerical methods for the achieving Y plus first cell distance. Here I choose 2 different contours to show you the result. The Y plus distributions after the solution is less than the 5 and maximum is 2.3. Also, the pressure distribution is obtained well. For the case of structural mesh and structural properties, since it's small, I use structured mesh. As you can see, there are 3 parameters L, H, and T. For grid generation, I use these parameters and generate meshes. Here we can see the change between LHT and the grid convergence of the solid domain. For this round, I just created 1 kilopascal difference between the top and the bottom of the structure and the displacement values obtained. I choose 270, 35, and 4 mesh. This one for continue. Here we can see the displacement vector and moment stress on the wing structure model with 1 kilopascal difference between top and bottom. For the FSI analysis, SU2 needs the new configuration file which couples between fluid and structural configuration files. We define it as a solver multiphysics and we need to say which configs we are looking for. Here I use 1 fluid and 2 different solid configs. And SU2 runs with coupled CFG. It then allocates between the fluid and solid CFGs, where fluid use solid as direct and solid can use admissives. Also here, there's an important factor that you need to define marker pressure and give it as a 0 Pascal load. And also you need to define marker fluid load. If you don't do this, it cannot solve what properly. Sorry, I am waiting it to change slides. Yes. After the FSI analysis, we can see that the aerodynamic coefficients are changed. The CFX, CFZ, and CMX values are important for us. The difference is nearly obtained by 0.7% for the after the deflection. And we can see that the wings before and after the FSI analysis. Before, you can see the orange one in the top 2 figures. And after the obtaining FSI equilibrium, it becomes like the gray one. And the maximum tip deflection is 1.2 centimeters. For the FFD box generation, we use SU2 def with the given configuration settings. It's important to use DV candidate FFD setting. And in my study, I use total 264 design points. After that, I simply obtain an Adjoint solution after obtaining FSI equilibrium. You can see the surface sensitivity contours in the right and bottom. For this case, I need to use continuous adjoint because when I choose to use discontinuous, discrete adjoint, it gives an error out of memory. So For my sources, I simply can use continuous adjoint. This is the point where my MSG study comes, but I need to show you one error. There, I faced an odd problem when I use rib spar configuration as a solid model. If I use RBF in the top left figure, the deformation interpolation, obtaining the solid deformation and matching it to the fluid domain becomes oddly deformed mesh. And I try to change all of the RBF parameters or other deformation parameters, but the changing did not solve the problem. So I try to use isoparametric method. With the isoparametric, it becomes like in between every rib on the fluid surface, it becomes a step-like structure. And also it comes like the Y-like step structure. I think it looked like this because on the fluid surface, it has 2 points on the solid structure which has equal distance. And it's my theory for this problem. What I need to do in the future is simply I need to define my objective function and I need to find way to put it in the optimization file. Either I use simple optimization methods like choosing drag and giving lots of constraints, or I can use some of the methods to convert constraint problem into unconstraint if it's possible. Also, it say that I need to define constraints as well. I need to complete the optimization and evaluate the results. Thank you for your attention. It's all for today. I want to listen your questions. If you are talking, I cannot hear. You might be muted.
Okay. Sorry, Emirhan, we were muted for a second. But I have a question towards your problem, and that is you have an FFD box set up, then you compute the sensitivities by the continuous adjoint method, and then you get the, I guess, to stay in SU2 terms, the objective function OF underscore grad file. And
Yes.
then you do a surface deformation, and then you get these kinks.
No, especially the surface deformation problem I obtained is just simply trying to morph the solid structure. I mean, I did it into the previous terms when I say that I see a problem with using ribbon spar structures. It's not after the obtaining adjoints and try to deform FFD box. It's before that.
Yeah, I do not fully understand the issue at this point, because I found FFD box deformation to be pretty good, but it seems like you're using something different, which I might not have understood. But that's all right. I would have to ask you directly.
Thank you, Tom. Other questions? Oh, yeah. So who they are.
Can you hear me?
Yes.
Okay, so when you showed the surface mesh for the blade, I think at the leading edge it was all isotropic triangles. Is that needed by the deformation or so the FSI or?
I don't think it's really needed for the FSI deformation. I just used unstructured mesh for all the domains and surfaces.
Yeah, but in pointwise, you can use T-Rex also on the surface. So for the leading edge, maybe it will lead you to a less number of points for the grid, and can help at the leading edge also. And I wonder if it was just needed or not to use isotropic.
It's not needed. I can try.
Okay.
Thank you. Other pending questions or burning questions, also from the online audience, if there is anyone connected. If not, I will thank again the speaker